I'm working on a near-field setup, and the main point is that basically we use this for high microscopy, high resolution microscopy, and in order to do that we need to drive a tip really close to a surface. So in order to do that we actually need to have a good control of the distance between this tip and the surface. In the specific case, the distance between them has to be in the range of 10 nanometers. So, okay, the natural question is how you do that? And the answer in this case is this. So what you see here, this is a so-called tuning fork. So basically, it's a piece of quartz made of these two parts with some electrodes on top, and this is basically a resonator. So on top of that is glued a piece of optical fiber, and at the end, at the very end of this optical fiber, there is the part that I was talking about. So the reason why I'm using this is because this resonator has a specific resonance frequency. So as long as it goes closer and closer to the surface, there is a shift of this resonance, and controlling this shift, it is possible to keep the tip at a fixed distance. So one can basically scan the surface. This is the main point. So basically this is the tuning fork with the two parts. This is the resonator I was talking about, right? And this is the optical fiber with a special tip fabricated at the end that has to be glued on top of it. But basically these are two USB digital microscopes, and they can be connected to a laptop, and the point is that they can allow me to measure with a sub-millimeter precision the overlap between these elements, and also the distances, the fact that the elements are parallel or not, or even you can actually see, I have a movie about that, you can actually see the glue, how the glue is spreading between the elements. So basically I usually put here 2 small drops of glue, because then what happens is that this part has to be glued on top of this arm of the resonator, and then basically this glue can be UV treated in order to be hard. And this makes of these 2 components a single resonator at the end, and then this is ready basically for the measurements.
So here we have a platform for holding the optical nano antenna. The piezoelectric tuning forks, which is the same thing you find inside a quartz watch, which have been glued onto a little steel plate. Normally what happens next would be we attach an optical fiber glued along one leg of this tuning fork, and right at the end of the tuning fork would be the optical antenna, which would be fabricated out of a metal such as gold, right on the end of the fiber. So this is basically the platform to hold the antenna in place above our sample. So once the fiber is glued onto this tuning fork, we place it on top of what could be called a normal optical microscope. So here you see where the platform for holding the optical fiber and the nano antenna is inserted into our microscope system, and this is attached then to a piezo scanning stage, which allows us to position in X, Y and Z dimensions our nano antenna, and the feedback system of this vibrating tuning fork allows us to control the distance down to just a few nanometers above the surface of our sample, or whatever we want to look at. So basically, whereas normal microscope is limited to the diffraction limit of light, by putting this optical antenna very close to what we're trying to look at, the light becomes trapped onto the nano antenna and confined to spaces much smaller than it is in free space, so say 10 times smaller. So instead of limited to something the size of 500 nanometers, we squeeze the light into a volume of say 50 or 40 nanometers. And by doing that, we gain resolution in the image we collect. So we can scan our antenna step by step over the sample we're looking at and build up an image which has a resolution greater than 10 times what you would expect with a normal microscope.